Hello everyone, I'm Seiichiro Tani. I'm going to talk about a quantum algorithm for finding the optimal variable ordering that minimizes the binary decision diagrams. You can get the full version at archive here. Let me briefly introduce the background of this study. I will later introduce more of the background. An ordered binary decision diagram, in short OBDD, is a graph representation of a Boolean function, like this. This has been extensively studied in both theoretical and practical fields. And one of the most crucial problems is how to find minimum OBDD for a given Boolean function. This is very difficult actually, and NP hard. The trivial complexity bound is about n factorial. But it is still important and interesting from theoretical and practical points of view to find an exponential time algorithm that works much faster than the trivial brute force algorithm. The only non-trivial algorithm runs in about 3 to the n time, which was discovered by Friedman-Supowit 30 years ago, where polynomial factor is hidden in this symbol. In this talk, we would like to show that further speed up is possible if we can use quantum computers. Here's the outline of my presentation. First, I introduce OBDDs and define its central problem. Then I review Friedman and Supowit algorithm. Then I illustrate the basic idea of our algorithm, which is a way of decomposing FS algorithm. Based on the idea, I show an elementary version of our algorithm and then generalize it to obtain the actual algorithm. Finally, I summarize my talk. To define OBDDs, it will be easy to consider the binary tree representation of Boolean functions. Let's consider this function that is just inner product function and consider its binary tree representation that is a single-rooted DAG directed acyclic graph with two kinds of terminals, false and true. And this is leveled graph in the sense that each level is associated with the same variable. For instance, every path from the root to a leaf corresponds to an assignment to the variables. If x4 is 1 and x3 is 0 and x2 is 0 and x1 is 1, then we can get fourth as a function value. As you can see, there may be many isomorphic subgraphs in the binary tree representation. For instance, these three green subgraphs are isomorphic and blue subgraphs are isomorphic. The basic idea of OBDD is compressing binary tree by sharing isomorphic subgraphs and removing other redundant structures to some fixed rule. For instance, by gradually sharing isomorphic subgraphs like this, we can get an OBDD. So ordered binary decision diagram is a leveled DAG defined for a Boolean function, and any node in each level is associated with the same variable. Now we introduce the most important notion, variable ordering, which is defined in this talk as a reverse ordering of variables to be read. In this example, the variable will be read in this ordering x6, x5, 4, 3, 2, 1. So the reverse ordering will be x1, 2, 3, 4, 5, 6. This is variable ordering. And it is easy to see that we can identify a variable ordering over n variables with a permutation over n elements. It is known that for a fixed Boolean function f and a fixed variable ordering phi, the OBDD is uniquely determined up to isomorphism. This is very important property because it is easy to check the equivalence to Boolean functions given as OBDDs by just checking isomorphism between them. And we can efficiently perform logical operations such as AND or over OBDDs. So for decades, OBDDs have been used in various practical fields such as VLSI design, formal verification, optimization of combinatorial problems, and machine learning. However, there is a crucial issue when using OBDDs. That is, OBDD size depends on variable ordering. Here are two OBDDs represent the same function but with different variables. As you can see, the sizes are very different. So we are interested in how much the variable ordering can affect OBDD size. The answer is as follows. The size of OBDDs can change exponentially depending on variable orderings. So the time required for OBDD-based operations, such as equivalence check and logical operations, can change exponentially. So it has been central how to find a variable ordering for minimum OBDD and how hard it is. For instance, let's consider a natural extension of the example we just saw to the case of n variables. For this variable ordering, we get OBDD with size linear in n. But for another, we can get exponential size. Actually, this is not a rare phenomenon. You can easily come across similar situations. Now we are ready to define the optimal variable ordering problem given a representation of Boolean function f, such as CNF, DNF circuits, and OBDDs. And the goal is to find the optimal variable ordering, that is, a variable ordering that minimizes the OBDD representing f. We will show a quantum algorithm for this problem. We can define the decision version naturally, but in this talk, we do not deal with the decision version. Let's quickly review the hardness result of the problem. If the input function is given as CNF, DNF, and logic circuit, then it is easy to show that the problem is NP-hard by Turing reduction from SAT. But if the input function is given as OBDD, The hardness is non-trivial, but it can be shown to be NP hard, even if the input function is restricted to monotone functions. Also, the approximation seems very hard. That is, it was proved that there are no polynomial time approximation scheme under the conjecture that P is not equal to NP. Therefore, there are numerous heuristics for practical use, but they have no non-trivial time bound. Finding optimal variable ordering is still important practically as well as theoretically in order to judge the optimization quality of heuristics or minimize intermediate OBDDs used while performing heuristics. Brute force algorithms find optimal variable ordering from n factorial possibilities because there are n factorial permutations over n elements. So time is lower bounded by n factorial. Only the algorithm with non-trivial upper bound is the one discovered by Friedman and Supowit. Its running time is about 3 to the n time, which is less than brute force bound. Our result shows that further speedup is possible if we have quantum computers. That is, there exists a quantum algorithm that, given representation R of Boolean function f, outputs the minimum OBDD for f together with optimal variable ordering in this time and space bound with exponentially small error probability, where R is a CNF or DNF circuit or OBDD. We have a few remarks on this result. First, our algorithm assumes QRAM. That is, it is possible to coherently read from and write into quantum memory. And our algorithm has an exponentially small error probability, while FS algorithm is deterministic. So this seems a bit unfair, but there are no non-classical probabilistic algorithms that beat FS algorithm. Third, our algorithm outputs the OBDD that is not minimum with exponentially small probability. However, it always outputs a correct OBDD representing the given function. Next, I will show you the idea of our algorithm. Roughly speaking, our algorithm is a kind of quantization of the algorithm given by Friedman and Supowit. So we start with their algorithm. Here's a key property of OBDDs, which is the starting point of FS algorithm. Once we fix a set of k variables for the bottom k levels of the OBDD, the minimum size of the bottom k levels and the corresponding variable ordering within the k variables are determined. So, for any k element subset I, we can define min cost I, which is the minimum size of the bottom k levels, and pi I, which is the corresponding ordering within I. So our goal is to compute min cost and pi for the entire set. Based on the property, Friedman and Supowit prove the following lemma. Lemma says that for any k-element subset I, min cost I and pi I can be computed from min cost j and pi j over all k-1 element subsets j of I with extra sum computation. For instance, if we assume I is a set of 1, 2, 3, 4, 5, then min cost I and pi I can be computed from min cost j and pi j for all 4 elements subset of I. This suggests an algorithm that computes min cost I and pi I for all subsets I in the non-decreasing order of the size I. More concretely, for k is equal to 1 to n in this order, for every k element subset I, compute min cost I and pi I from min cost j and pi j over all k-1 element subsets j of I with extra 2 to the n minus k time computation. Its analysis is rather simple. The number of k-element subsets I is n choose k by the definition, and for each k, roughly the n choose k times 2 to the n minus k time is required. So the total time is the sum of this amount over all k, which is 3 to the n, up to a polynomial factor. We can schematically view the FS algorithm. There are n vertical lines here, and on each line k, there are n choose k dots. Each dot represents the pair of min cost I and pi I for a subset I of k elements. Then FS algorithm computes each blue dot from k-1 red dots, because this k-1 red dot is a k-1 element subset of I. And this procedure goes from left to the right, from the dot for empty set to the dot for the entire set. Now let me show you the basic idea of our algorithm. This is based on decomposition of FS algorithm. First, take a dot I. We call this neck because it seems necked in this figure on the line k for some k defined later. Then compute min cost I and pi I only for neck I. This can be done with generalization of FS algorithm. We call this FS star. So this computation corresponds to this yellow area. And then starting from the neck I, compute min cost n and pi n. And this computation can be done with, again, a generalization of FS algorithm. And this corresponds to this yellow area. Then finally, running this for every I and take the best one. Note that running this for a particular dot I may not give an optimal solution. So the time complexity is as follows. This part is for running this procedure for every I, and this part is for the second step, and this part is for the third step. And we replace n choose k with the square root of n choose k by using quantum minimum finding. Then this achieves a minimum 2.98 to the n by optimizing k, but this is very tiny improvement over FS algorithm. To gain further speed up, we increase the number of necks to get the second version. Then algorithm can be seen like this, where we perform the quantum minimum finding recursively. Then we get the time complexity about 2.83 to the n by setting 6 necks appropriately. Then make the second version composable and use it as a subroutine to get a third version. We recursively apply the same argument and obtain the final algorithm. The final algorithm has the time and space complexity of about 2.77 to the n with exponentially small error probability. Our algorithm has some similarity in structure to unbiased Edwards algorithms presented Soder 2019, but there are some unique technical difficulties, so let me comment on those. First, the problems correspond to the yellow parts are not just scaled-down version of the original problem, so we cannot use FS algorithm as is for this. Instead, we need to generalize FS algorithm. And second, the right and left yellow areas are asymmetric in terms of complexity by the property of OBDDs. So we need to take this asymmetry into account when optimizing the value of k. Now let me summarize my talk. Ordered binary decision diagrams have been studied as important data structure for Boolean function manipulation. A most central problem on OBDDs is the optimal variable ordering problem, which is almost equivalent to OBDD minimization. And the Friedman-Supowit algorithm achieves about 3 to the n time, which is much faster than brute force algorithm. Our results show that further speedup is possible with quantum computers. Actually, our quantum algorithm runs in 2.77 to the n time. Here's some open questions. The first question is trivial, asking if it is possible to significantly improve the complexity. Our algorithm, as well as FS algorithm, constructs a minimum OBDD to find the optimal variable ordering. The second question asks if it is necessary to construct the minimum OBDD to obtain the optimal variable ordering. Our algorithm always outputs a valid OBDD for given function. The third question asks if the problem becomes easier if you are allowed to output an erroneous OBDD with a small probability. The last question is about time-space trade-offs. It is easy to see it is possible to reduce the space complexity if you relax the time complexity bound. The last question is it is possible to say anything about time-space trade-offs. Thank you for listening.